Hi everyone, Dr. Daugherity here, physics professor at Abilene Christian University. I was in class this week and I ran across the weirdest looking circle that I've ever seen. I wanted to share it with you. Let's check it out. So if I start with a two-dimensional circle, then you know it's got a surface area, that's a circumference, of just 2 pi r. And if I bump up to 3 dimensions, like a sphere, then I've got a surface area of 4 pi r squared. But what about something arbitrary, like we needed in counting these quantum mechanical states of an ideal gas? Well, it turns out the mathematicians have figured this out for us. You know, they're useful to keep around. You just put them in the basement and keep throwing coffee at them, and they'll give you some good results that you need. The answer turns out to be 2 pi to the d over 2 power times r to the d minus 1 over d over 2 minus 1 factorial. I think it's pretty obvious if you're just going to look at it. Well, okay, we don't trust anybody, so let's check and let's see how well these things are going to work out. So let's check our results. Okay, so what about for 2 dimensions? Well, if d equals 2 and I use this equation down here, so I'm going to have a 2 times pi to the 1 times r to the 1 over 1 minus 1, which is a 0 factorial. Well, okay, let's stop here for a second and figure out what that is. So you all remember factorials, right? So factorials are the repeated multiplication thing. So like 1 times 2 times 3, all the way up to some n, and that's n factorial. So I've got like 1 times 1 or something is 1 factorial, and 2 times 1 is 2 factorial, and 3 times 2 times 1 is 6. So it turns out to fill out the pattern, 0 factorial is 1. Okay, well, we'll go with that. So, cool. So I've got 2 pi r to the first power over 1, so that's just 2 pi r, which is the circumference, the surface area of our circle. Okay, cool, d equals 3. So going back to our little equation down here, I'm going to have a 2 pi to the 3/2 power r squared. R squared looks promising. 3/2 minus 1 factorial. Oh dear. Okay, so I'm going to have a 2 pi 3/2 r squared. 3/2 minus 1 is 1/2 factorial. Okay. Well, again, mathematicians to the rescue here. So if I were to take our factorials and kind of plot them out, so I've got 0, 1, 2, 3, 4. Okay, 0 factorial is 1, and 1 factorial is 1, and 2 and 3 factorial is 6. Well, mathematicians have figured out a function that kind of fills this in and connects all these dots together. It's called the gamma function. It lets us evaluate factorials for like non-integers and negative numbers and complex numbers and all sorts of weird stuff. And it turns out that 1/2 factorial equals, and again, I think it's pretty obvious, square root of pi over 2. Okay, so what have I got? 2 pi to the 3/2 r squared over pi to the 1/2 divided by 2. Well, I move that 2 upstairs. A pi to the 1/2 cancels from top and bottom, and I get 4 pi r squared. Awesome. Okay, so now we're going to use this. I want to go back and think about a weirder thing. Let's make it even worse, or better, depending on how you think about it. So what about a one-dimensional thing? This was kind of a question that came up in class. So, all right, well, let's try this. If I just plug in d equals 1, what do I expect here? Well, okay, 2 pi to the 1/2 r to the 0th power over 1/2 minus 1 factorial. All right, so I'm going to have a 2 pi to the 1/2 power. R to the 0 is just 1, so that goes away. Negative 1/2 factorial. Well, okay, so the factorial, like, it is worked out for negative numbers too. And what does negative 1/2 factorial mean? That's another video. I don't really know. And left of this graph, it goes completely bonkers. It goes like this. It's actually like infinity or negative infinity at the integers. But again, the mathematicians have worked out that this thing is the square root of pi. So I get 2 pi to the 1/2 over square root of pi, which is also a pi to the 1/2, and that's just 2. So apparently the surface area of my one-dimensional thing is 2. And there's no like radius dependence. It's just 2. Okay, so that got me to thinking about this. So check it out. Suppose I start with the circle and I define some kind of radius r. Well, the circle, I could think about it as the collection of all the points that are equidistant from the center. And that would give me a 2-dimensional thing. And that works in 3 dimensions beautifully. So I define some kind of radius r, and I draw my 3-dimensional sphere. 3-dimensional, so there we go. That's 3D. Okay, well, what about in 1D? Well, okay, I was thinking about this. So let's suppose that this is the center of my circle. And I define some radius r. And if I'm on a 1-dimensional line, I guess I'll do this purple one here. If I'm on some 1-dimensional line, I've got 2 choices. I can be either r to the right, or I can be r to the left. So I can be either here or here. I've got 2 places to go. And so my surface area, when I count, it's 1, 2. Okay, last thing that made me convinced that this is actually real and not some kind of gibberish. Let's think about volume. So everybody knows that the area of a circle, the volume in 2 dimensions, is going to be pi r squared. And if I take the derivative, this just becomes 2 pi r. Okay, nice. So the volume of a sphere, 4/3 pi r cubed. I take the derivative, I get 4 pi r squared. What's the volume? Well, the volume would be the region in between my equidistant points, which is the distance from here to here, which is just 2r. I take the derivative with respect to r, and I get a 2. So with all of that said and done, I think I've convinced myself, and maybe even you too, that this is a circle, that is a 1-dimensional circle, with a surface area of 2. I thought that was really cool. Thanks for watching.